Hi everyone, today we're going to be talking about the discrete Fubini's principle. In essence, we're dealing with, in this theorem, cases of two nested sums. And what we want to do is we want to exchange the order in which the indices occur. So if we have something like this particular nested sum, so I equals 1 through m, and then j equals 1 through n, we want to know when we can put the j before the I. What would the sum look like if we were to do that? So I'll tell you what it is and then I'll prove it. In this case, we have j equals to 1 through n and I equals to 1 through m. So really we were able to exchange these two sums without any hassle. But it's not always the case that it's so simple. And we'll get into a more complicated example in a moment. But let me prove why this is true. What we're going to do is that we're going to use a matrix representation. And for those of you who haven't done any linear algebra, don't get scared, because we're not actually going to be using any matrix operations or linear algebra. We're just going to be stacking things in a box. What do I mean by that? Well, in this sum and the original sum, there are m times n terms. So this looks like a prime example of when we can have a box with m rows and n columns, and we're going to fill it up with entries. Let me show you what I mean exactly. We have A11, A12, and by the way, this isn't 11 and 12. There's actually a hidden comma in here. I'm just not putting them in there because in linear algebra it's simpler to write it without the commas unless you absolutely need to. We have A13 all the way through to A1n. Then we have A21, A22, A23 all the way through to A2n. We have A31, A32, A33 all the way through to A3n. And now we're going to put in the ellipses here because we can't possibly write all the rows. We have AM1, AM2, AM3 all the way through to AMN. And so you can see we've got this matrix of m times n values. What's going on in the sum is the following, and by the sum I'm referring to this. So on the left side, let's look at the inner terms first. The inner sum has I fixed. I is fixed because we fixed it when looking at the counter for the outer sum. I is fixed. So inner sum is a row. So we have something like this. This is the second inner sum. on the right over here, J is fixed. And by the way, when I say I is fixed or J is fixed, I'm referring to in the inner sum, not in general. In general, I and J are iterating as counters. So in this case, inner sum is a column. And an example of a column is this. So it doesn't matter whether we're iterating through the rows 1, 2, 3 all the way through m, or if we're iterating through columns 1, 2, 3 all the way through the end here, the nth column. In the end, we get all m times n entries in the sum. So one is a matter of adding up rows, and the other one is the matter of adding up columns. And this is the essential idea behind the discrete Fubini's principle. Unfortunately, it's not always as easy as what we just did a moment ago. So let me show you some harder examples. So the problem is the matrix might have lots of 0 entries. And this usually means a triangular matrix. Let me show you what I mean by a triangular matrix. There are 4 principal examples, although you can have some variations that I'll briefly mention in just a moment. Usually I'm drawing rectangles, but really I should be drawing squares. So let me backtrack a moment and draw squares, because really we're dealing with square matrices. One, 2, 3, and 4. So the first example is this one, where we have the upper right triangle filled with numbers, and there are zeros in the bottom left. The second example is where the bottom left is filled with numbers and we have zeros in the top right. And there are 2 more examples. The first one, or rather the third one, is where the top left is filled with numbers and the bottom right has zeros. And finally, as you have probably predicted, the final example is where the bottom right has numbers, and they could be zero, some of them, but the point is we're emphasizing them, whereas we're ignoring what's on the top left. Now I'm not going to go through how to deal with all of these, but we're going to show how to deal with the first one, and that should give you enough inspiration to figure out the rest of them. So let me show you what kind of a matrix this first one looks like. We have A11, A12, A13, all the way through to A1n. Then we have A22, A23, all the way through to A2n. We have A33 going to A3n. And we keep going this way until we're left with only a, n, n in the final row. And notice that here m equals to n because it's a square matrix. So we have a matrix like this, and in the bottom left, these are all zeros. So we're gonna not mention the bottom left entries in the sum. So let's see two ways of writing the sum, one by iterating through rows and the other by iterating through columns. So iterating through rows, this is what it looks like in this case. We have the sum of I equals to 1, because from 1 through n, because we're actually going to be going through every row. So we do go through all the i's, whereas for the j's, for each row, we go from the ith value, so we start an I in each row, and we go all the way through to n. Whereas if we're iterating through columns, we get the following nested sum. We start with j equals to 1 through n, because we are going through every column. But what happens with the i's is that they start with 1. As you can see, we're starting in each column with the 1 in the first entry, but we're only going up to j. See, we stop here, and we stop here, and we stop here. So what that tells us is that the sum of I equals 1 through n, nested with the sum of j equals I through n of aij, is equal to, when we swap j and I, we get j equals to 1 through n, and I equals to 1 through j of aij. So hopefully that shows you how to deal with this one here, and I think you'll be able to figure the other three out. I just want to mention that the discrete Fubini's principle can get a bit complicated, and there are other examples where we iterate through rows versus columns, or we switch between the two. One example is a matrix of modular congruences, and this comes up in the generalized Chinese remainder theorem. Another example is in the proof of the associativity of generating functions, that is the associativity of their multiplication. And finally, there's another example, which is the associativity of the Dirichlet convolution of arithmetic functions. And these all use variations of the discrete Fubini's principle. Now, my main point here is that you should not memorize formulas. What you should do instead is use your sense. What do I mean by that? What I mean is that you need to ensure that each term of the matrix occurs once in the sum. And the final thing that I want to leave you with is that the sum might as well be a product, because everything we've said works for products as well. Okay, so let's do a summary of what we did. We first stated the discrete Fubini's principle for the most basic case, where we can simply swap the two indices, and we showed that this is when we have a full matrix. Then we looked at an upper triangular matrix, an upper right triangular matrix, which was this one, and we showed what happens if we're ignoring what's on the bottom left. We iterated through the rows and we iterated through the columns, and we came up with this formula. And finally, I mentioned a few cases in which you have to use your sense of mathematics instead of just using a formula, which includes a matrix of modular congruences, the associativity of generating functions, and the associativity of the Dirichlet convolution. So in general, do not memorize formulas, and remember that if you do come up with a formula or an idea, it works for both sums and products. Okay, thank you for watching, and I'll see you next time.